All right, I'll begin. Heavenly Father, we thank you for this day. I thank you for the beautiful weather outside and for all the fall colors and everything. And just pray for these students that they would understand the material, that we would glorify you in what we do this day. And we just thank you again for your many blessings, Lord. In your name I pray, Lord Jesus. Amen. So, I guess I need to do some more examples for you guys. Are there any questions about anything in particular? Yep. Yeah, you can ask questions about the homework, sure.
I mean, like the long division one.
The long division one? Well, you'll have to be more specific.
Like you said, you wanted us to do work on, right?
Oh, he's talking about the information.
Oh, I do need the participation assignment to be turned in. That's true. If you want to turn them in, that'd be good. So if you hand them over, I'll collect them. Thank you.
Thank you.
Uh-huh. If somehow this has still escaped your attention, if you can get it to me by the end of the day, I will still be happy. What's that? The videos are on the YouTube. If you can't find something, you just email me, I'll tell you. So the emails are in the YouTube playlist. If you go back to like last week, they're at Wednesday. So if you go to the initial Canvas announcement, the first Canvas announcement I made this semester, there is a link to the YouTube playlist. Okay, and everything that I have taped for this class is on there. So if you still can't find it, just like email me. I'll send you a link. Okay, so did you have a question about something else, or was it just about that? Okay. So one of the things I talked about in the videos that some of you have seen, some of you have not, I'm guessing, is the issue of complex roots, right? I've talked a little bit about complex roots. I should talk a little bit more about it just to make sure everybody's on the same page. So what's the deal with complex roots? So complex roots, let's talk about them. So there's a theorem. All right, if f of x is real polynomial, all right, and f of alpha plus I beta is equal to 0, where alpha and beta are just real numbers with beta not equal to 0. So in other words, it's a complex number, all right? So if you have that, when you plug a complex number into the formula, you get 0, then there's a few things that happen. One of the things that happens is that alpha minus I beta is also equal to 0. And more than that, in fact, what you get is that x minus alpha minus I beta times x minus alpha plus I beta is a factor of f of x. See, the factor theorem for this one gives us this factor, right? The factor theorem for this one gives us this factor. But what's more interesting is what happens when you multiply those two factors out. What happens when we multiply these out? Let me just do it for us. We multiply these. We get x minus alpha times itself, and then minus I beta x minus alpha plus x minus alpha times I beta, and then minus I squared beta squared. So something really cool happens there, namely that the part with the I cancels out. See the middle part? These two terms are the same. They cancel. And what is I squared? I squared is equal to minus 1, remember? I squared is minus 1. So all of this simplifies simply to x minus alpha quantity squared plus beta squared. All right, so in other words, every zero to a polynomial which is complex, if you have a complex zero of a polynomial, when you plug a complex number in, it gives you 0. That means that that polynomial has this prime factor. It's a prime factor of f of x. I guess I need to say the words here. The following is a factor. Factor of f of x. All right, so like, let me show you how this works for a concrete problem that's not too onerous. And I think there's a problem like this in your homework, in like the website, listen to me, website, in the MyLabs, right? So like, here's one. We could look at f of x equal to, let's say, x cubed, all right, plus 4x squared, all right, plus 5x. We could look at that, and we could calculate what is f of, let's do a couple calculations here, all right? First of all, let's try f of, let's say, 2 plus 3i, all right? Let's work that out. I think this is actually a little bit harder than what's in your homework, okay? I think the ones in your homework, like I think the homework one has a quadratic here, not a cubic. But if we can do this one, we can do the homework one. So how do you do, what does this mean? We take 2 plus 3i, and we take it to the third power, plus 4 times 2 plus 3i squared, plus 5 times 2 plus 3i, right? So how's that work out? Let's see here. We've got 2 plus 3i times something. I'm gonna put brackets here. I'm gonna come back to that, okay? Plus 4 times brackets. What's 2 plus 3i squared? I'm gonna run out of board if I'm not careful here. So if you don't mind, I'm gonna just jump up a line and do the 2 plus 3i squared on its lonesome. How's that work out? We get 2 times 2 is 4. And then we get 2 times 3 is plus 6i, plus 6i, plus 9i squared. So we just FOIL out like usual, just distributive property. All right? The new wrinkle is that I squared is minus 1. So since I squared is minus 1, this works out to 4 minus 9, which is minus 5, plus 12i. Okay? So that is what goes here. And it also goes here. See, because 2 plus 3i cubed is 2 plus 3i times 2 plus 3i squared. But we know that 2 plus 3i squared is minus 5 plus 12i. Right? By what we just worked out. And then the last piece, 5 times 2 plus 3i, that's easier. This just gives us plus 10 plus 15i. All right? Now we multiply out. We gotta distribute again, right? So we've got 2 times minus 5 is minus 10. 2 times 12 is plus 24i. We get a minus 15i. And 3 times 12 is 36. We have I squared there, okay? So that's the first, I'll do an underline. This term gives you these terms. All right, I'll do the rest of it in purple. 4 times minus 5 is minus 20. 4 times 12 is 48, so plus 48i, plus 10, plus 15i. All right? And what's I squared there in the middle? This is what? This right here is what? That's just -1, right? So let's put it all together. What do we got? So you add all the real parts together. So I've got a -10, -36, right? -10 minus 36 is -46, minus another 20, -66, plus 10, that's -56. So if I didn't make a mistake, -56 is the real part. What's the imaginary part? 24 minus 15 is 9, 9i. We've got 9i. 9 plus 48 is 57i. 57 plus 15 is 72i. All right, there it is. So what does this mean? What does this tell us? It doesn't really tell us anything because the theorem only gives me information about when I plug a complex number in and I get 0, right? I didn't get 0, I got this, so I don't get to say anything, all right? But the reason I did this was to illustrate how you evaluate a function at a complex number. You just plug it in and follow the formula, all right? Let's try a different complex number, same polynomial. Let's try to calculate f of, I don't know, -2 plus I. Let's see how that goes. All right, so we want -2 plus I cubed. What was the formula? Plus 4 times -2 plus I squared, right? Plus 5 times -2 plus I. Let's work that out. Now, we learned in the last calculation that it is a nice idea, it's a smart move, right? To take a second to calculate the square of the complex number as a starting move, right? Like if we calculate the square of the complex number, we're going to be able to use that to do the rest of this calculation, right? So, you got it. It's all good. So you guys tell me, what is -2 plus I squared? -2 plus I squared, what's this? Yeah, at the moment, all we've done is just I introduced this polynomial, and I said, let's plug this complex number into it and see how that works. How do we do that calculation? We did it. We found -56 plus 72i, and we said, okay, well, that's nice, but that doesn't really help us any in terms of algebra because the theorem gives us information when we plug the complex number in and get 0. But we didn't get 0. Maybe we'll get 0 this time. Let's see how it works. So -2 plus I squared, 4 minus 2i minus 2i plus I squared. So that is 3 minus 4i. And so what I get then is -2 plus I times 3 minus 4i plus 4 times 3 minus 4i. And then that last term I'll just multiply, right? 5 times -2 is -10. And then 5 times plus 5i, yeah? Any questions? Yep. How did I get 3 minus 4i? So here, 4 minus 2i minus 2i is the minus 4i. I squared is what? -1, right? So 4 minus 1 is 3. Yeah. Good question. So let's see here. Now we multiply. Multiply this, right? FOIL it out. And -2 times 3 is -6. Then I get myself a plus 8i, plus 3i, minus 4i squared, all right, from the first term. And then what comes next? Plus 12, minus 16i, minus 10, plus 5i. All right. I squared was what? Yeah, remember this is minus 1. So that is actually a 4, right? Okay, now let's add them all together. Add the real parts together, add the imaginary parts together. What do we get? I sure hope we get 0. Minus 6 plus 4 is minus 2 plus 10, minus 2 plus 12 is plus 10. 10 minus 10, 0. What about the imaginary part? 8 plus 3 is 11. All right. 11 minus 16, minus 5, plus 5, plus 0 times I, right? And of course, we just write that as 0. What does this tell me? If you believe the theorem, right? If you believe the theorem, so here I have, so identify my alpha, which is the real part of the root, is minus 2, and my beta, what's the coefficient of I here? It's just 1. Very good. So this means that x minus alpha squared plus beta squared, in this case, is x plus 2 squared plus 1. That has to be a factor, right? But what is that? You multiply it out, what do you got? X squared plus 4x plus 4 plus 1, which is x squared plus 4x plus 5. Is that a factor of f of x? Yeah, right? I mean, look at it. Can you see it? F of x is what? It's x cubed plus 4x squared plus 5x. We factor x out. There it is. So in fact, yes, it is a factor, and that's why when we plug that complex number in, we get 0. Let me work well, first of all, you let it settle, and you get the main theorem here is if you've got a complex 0, that means that the conjugate of the 0 is also a 0. The conjugate just means you flip I to minus I is also a 0. And since they come in a conjugate pair, when you multiply the conjugate pair factors, you get a prime polynomial factor. Yep.
Where'd you get the minus 2 plus, minus 2 plus I, did you just make that up, or did you, get it from somewhere?
Yes, I got it from comparing alpha plus I beta to minus 2 plus I. So I'm pattern matching. Yeah.
What happened to the cube of the negative 2 plus I?
So I rewrote this cube is minus 2 plus I times minus 2 plus I squared. And we calculated minus 2 plus I squared over there, so I just broke it into 2 pieces. I did the same thing over here. See, I took the cube and I broke it as the first times the square. So it was the same pattern as last time. But.
So it just happens to be the same as the negative 2 plus I.
Well, if you're going to calculate the cube of something, and something's complicated, it's a good idea to break off and do the square first, and then take the square and multiply it by whatever you're cubing, and that gives you the cube, 2 steps. We don't usually think about this, right? No one really thinks about this much. If you've got 5 cubed, how do you do it? You do 5 times 5 squared, right? So you do 5 times 5 first, you get 25. 25 times 5 is 125, right? It's the same thing here. It just looks more complicated because it's a complex number, but it's the same idea. Did I answer your question?
Yeah, well, on a test or whatever, are you going to be given the minus 2 plus I? Or are you going to have to figure that out?
Oh, interesting. Yes. What is your preference?
Well, I don't know. I just...
I'm...
Well, even on there, the 2 plus 3I, are you gonna... Is that going to be given to you, or are you going to figure it out?
Well... So, what do you guys think? Should I give it to you, or should I make you figure it out? See, I don't know what make you figure it out means exactly, in the sense that let me try to be more specific here. I'll be back with you. I'm creating our next example. Just give me a second here. So to answer your question with my next example, let me do that. So here's a typical test question that's based on this material. I'm gonna have to. Can you guys remember the theorem for me? Can I erase it? Actually, it'd be better if I could just erase this board. Is that okay now? I don't like working over here. I feel, I don't know. All right, so here it is. You're given, what's example 3? Okay, so f of x equal to x to the power 4 plus 17x cubed plus 101x squared, yowzers, plus 335x plus 250. I might be able to make a test problem with slightly smaller numbers, but this is what came to us right now, okay? Anyway. And then here's the deal. You're given, and let's see, I'm trying to figure out who will give you this information. A math wizard, there we go. Tells you that f of, let's see here, f of minus 3 plus 4i equals to 0. Factor f of x completely. That is more likely how this will come to you on a test.
Will be given that
Yeah.
in the F.
Well, there's another kind of question I could ask you. Example 4 would be something like this. You know, f of x equals to x squared plus 4x plus 5. Find two complex numbers for which f of alpha plus I beta is equal to 0, you know. That one, I could make you find it.
Okay.
But it has to be quadratic. Otherwise, it's terribly unfriendly.
Yeah.
Or either it has to be quadratic, or it already has to be arranged so that you can easily see a quadratic factor in it. Like this one, the answer is, well, this is x plus 2 squared plus 1. So from that, I can immediately see x equals to minus 2 plus or minus I. Make f of x equal to 0.
Okay.
Because that's the theorem. If we can complete the square to x plus alpha squared plus beta squared, x minus alpha squared plus beta squared, then I can read from this that there's a complex 0. That's still true even if it's a higher order polynomial. But the thing is, to be friendly, you really have to have like a quadratic factor sitting out on its lonesome to see. If that's not the case, I really need to have like a math wizard or something come and tell you information like that. And I really don't want to give the test question which says, decide if f of minus 3 plus 4i is equal to 0. Like, I have no interest in seeing you take this and calculate the fourth power of it, calculate the third power of it, multiply by 17, multiply its square by 101 and add 335 of itself, and then add 250, and see how many people here can work it out and get 0. No one wants to grade that. No sane person. Like, no. So I will tell, but the question is, okay, let's get back to example 3. I shouldn't say that that's the only way it can come to you. That's too strong a statement. There are other problems that are reasonable. I could ask you. I should try to find those. Yeah. Here? Because I'm looking at x plus 2 squared plus 1, and I'm comparing it to x minus alpha squared plus beta squared. And if you look at this, you can see alpha is equal to minus 2, and beta is equal to 1 by comparison.
So, like,
Pattern matching.
became a negative 2.
How can I make x plus 2 be x minus alpha? I must make alpha equal to minus 2, right? So it's the same pattern matching we do with factoring, right? If you've got an x plus 3 in your factorization, that means minus 3 is your 0. Same juxtaposition of signs. Yeah. I will get back to example 3 eventually. You guys will not distract me. Yes?
So we can expect to see a test question like example 4?
Yeah, I would assume so. Something, or example 3.
Would you mind walking through that problem a little bit slower?
Yeah, sure. So if I'm dealing with, if I'm given a quadratic, right? So let's see, first of all, what was the problem? The problem, as stated, didn't have this. This was the problem, okay? That was the problem. F of x equals that. Find two complex numbers for which, you know, let's say f of x equals to 0. There, okay? I mean, call the complex numbers x. Maybe I'll call the complex number c so we can get a better sense of the difference here, c. F of c, all right? So c. That complex number is 0. Okay, so the logic is simply this. If you're looking for complex numbers of a quadratic, you complete the square. Completing the square on x squared plus 4x plus 5 is x plus 2 squared. I subtract 4, I add 5. That leaves me with 1. So this is completing the square. And then I go back to my theorem. The theorem simply says that anytime I have a term squared plus another constant, I can identify that as coming from being a complex 0. And so like I complete the square and then I compare to this. And from that I can read that my real part was minus 2 and my imaginary part was 1. That's it. I'm using the theorem over there. If you want, another way to do this would simply be to use the quadratic formula, right? Because you're just solving x squared plus 4x plus 5 equals to 0. How do you do that? You could use the quadratic formula, right? If you don't like using my theorem, which I think is easy, you can of course also just solve x squared plus 4x plus 5 equals to 0, and that will give you x is equal to, you know, minus 4 plus or minus the square root of 16 minus 4 times 5, which is 20, over 2, which gives you minus 4 plus or minus the square root of minus 4 over 2, which is minus 4 plus or minus 2i over 2, which is minus 2 plus or minus I. So you could also do this problem that way if you like. But this is much more difficult a calculation than just comparing this and reading directly alpha equals minus 2, beta equals 1. Right? What?
Oh, I'm sorry.
No, you can, I mean, comments are allowed.
I was saying, it actually kind of looks easy to me.
The quadratic equation looks easier? That's because we're familiar with it, right? I'm trying to get you to learn something new. So. I'll do another one. I think there's still some unrest. Example 5. We'll eventually come back to example 3, I promise. So suppose you had f of x equal to x plus 3 times x squared minus 10x plus 27. I say find a complex 0 of this polynomial. You know, complex solution of f of x equals to 0. So the way I would do this is I would say, okay, well, the complex solution has to be the solution which makes the second factor be 0. Right? The only way to make the first factor 0 is to make it -3. -3 is not complex, so that's not it. Right? So I must need the second factor is 0. And to understand the second factor, I can complete the square. Completing the square gives minus x minus 5 quantity squared. All right. Minus 25 plus 27. All right. Clean it up. This is x minus 5 squared plus 2. All right, so let us, one more step, make sure we're on the same page here. We do x minus 5 squared plus the square root of 2 squared. All right? At this point I go, aha, my theorem applies. Anytime I complete the square, I have a sum of squares like this. That means it's a complex root. And I can read the complex root directly off this formula, because I can compare this to x minus alpha squared plus beta squared. And if I look at this, I can see, aha, alpha equals to 5, beta equals to square root of 2. So the answer is 5 plus I root 2. F of 5 plus I root 2 will be equal to 0. Yep. Well, I need to compare to this form. So in order to see what beta is, I need to understand this number as being a square of something. Like, we didn't see it so much in the past example because we were comparing 1 to beta squared. So like, I mean, 1 is 1 squared, so it's kind of like a special, you don't really see it there much. Here, I had to look at that as, it's just this. If I want 2, you could look at it this way. If I want 2 to be equal to beta squared, that makes the square root of 2, well, plus or minus the square root of 2 to be equal to beta. So there is, in fact, another answer, right? Because if this is true, it's also true that f of 5 minus I root 2 is equal to 0. So you can't get one without the other. The complex zeros, they always come in these conjugate pairs. Yep.
Where did the I come from since the square root of 2 is positive? Because I thought you'd get an I only if the square would be.
Yes. So it's from the theorem. The answer to your question is to derive the theorem. I'll do it in this case. So here, this is equal to x minus 5. So I squared, right? That plus I can trade for a minus I squared. Watch this. See, minus I squared is minus 1, which is 1. So I have not changed it. If you take I times the square root of 2 and you square it, you get minus 2 times minus 1 gives us back plus 2. Like, this is equal to that. Okay? And because of that, we have difference of squares. So we can go back to day 1 and factor. So whenever we have x minus alpha squared plus beta squared, to factor it, we have to introduce I. That gives us a difference of squares. Then we factor it, and we get complex roots. The factor theorem still applies. This is 0 when x is equal to 5 minus I root 2. This is 0 when x is equal to 5 plus I root 2. Which, of course, are the two zeros that I claimed by the theorem. How do you prove the theorem? By factoring. My point is, you don't have to factor every time you see one of these. If you know the theorem, you can just read off the solution. All right, so now let's go back to example 3. Here the question, so this question is picking your brain about this theorem in the other direction. I give you the complex zero, right? I'm asking you to use that to find a factor. See, it's the other direction of the thought. So what does it mean? We have f of, what does this mean? F of minus 3i, minus 3 plus 4i equal to 0. What does that tell us? That tells me that x minus a minus 3 squared plus 4 squared, also known as x plus 3 squared plus 16, is a factor of the polynomial, right? That's what the theorem tells us. Every complex zero corresponds to a prime factor of that form. Oh, you got me. Okay, cool. Now, let's multiply it out. What is that? So this is x squared plus 6x plus 9 plus 16. X squared plus 6x plus 25. So that is a factor of f of x. What's that mean? That means that we can write f of x is equal to x squared plus 6x plus 25, right, times something. How do you find the something? Right? I mean, to put it up here, this is equal to, x squared plus 6x plus 25 times something. What on earth is the something? Yeah? Exactly. That's the right thing to do. Divide it. That is the secret sauce. Long division. Divide it. The something must be f of x divided by x squared plus 6x plus 5, right? So the way we do that is like so. Now, if you are a algebra ninja, you probably could just factor it just straight up. If you're such a person, lovely. I'm glad you're here. Can you tell me what the something is without doing this? I can tell you two parts of it. I can tell you that there's an x squared here, and I can tell you that there's a 10 over here. But what goes in the middle? That's the See, I know that x squared has to be here, because x squared times x squared gives me x to the fourth. That's obvious. And the only way to get to 250 is from the constant term of the something times the 25. So you have to put a 10 there. But man, what to put in the middle? That'll bend your brain a little bit, right? And you can just kind of try guessing numbers until you find something that works. But that long division is a more safe path here. So we have to divide, what was it? X squared plus 6x plus 25 into this. And so how do we start? X squared, very good. And then x squared times this gives me x to the fourth plus 6x cubed plus 25x squared. We take the difference, all right? And 17 minus 6 is 11x cubed. And then 101 minus 25 is 76 x squared. And then we got plus 335x plus 250. I bring it down now. Some of you bring it down later. Whatever floats your boat, all right? As long as we agree on the answer. So, and if you, if you really, really are like in love with the book and you just want to do this problem with two complex synthetic divisions, you're free to do it. But I'm not going to teach that to you because this is a better way. Okay, so plus 11, 11x, right? I need the 11x there to get this 11x times x squared gives me 11x cubed, which I want to get rid of, right? So I'm not going to use that green marker. No one can see it. Use a black marker instead. So plus 11x. So we get 11x cubed. 11 times 6 is 66, yeah? X squared. 11 times 25 is 250 plus 25, which is 275. And yeah, we have to subtract that. What happens? We get 76 minus 66. That's not bad. That's 10x squared. Oh, man, this marker is so nice. I wish they were like, they're good for about like the first 10% of their life, and then they're just kind of like, It's kind of like humans. Let's see here. Anyway, let's see. 335 minus 270. That's not true. What's that? 60. Okay, thank you. Saving me from thinking. I appreciate that. Plus 250. And then what's next? Plus 10, right? So apparently, the thing that was going to bend my brain was putting an 11 in the middle, right? Apparently, it's an 11x. Let's make sure it goes. So we got 10x squared, 60x, 10 times 25 is 250. Remainder is 0. That's good. We really needed to see that. So there you go. We have factored it completely. Well, did we factor it completely? Hold on here a second. So what we got is f of x is equal to x squared plus 6x plus 25 times x squared plus 11x plus 10, right? Can we factor? Is this factored completely? I mean, we know part of the story here, right? The first part of it's prime, yeah? And I should say factor completely over the reals, okay? That's what I'm talking about. So would you say the second one, what happened? It can be factored. How's it factor? Yep, and there you go. That's the answer right there.
Did you make up this equation in your head?
No, that's why I had to get the computer. I mean, yes, of course. I made it up on the fly, like all of my examples.
You never know.
No, what I did was I multiplied this one times that. I know that this has a nice complex solution, and I know that this can be factored, which made this last part of the example interesting. But I also know my limits. I know that multiplying x squared plus 6x plus 25 by x squared plus 11x plus 10 is not something I'm going to try to do in my head. There are 9 terms from that.
You're a math wizard.
And they have to, I'm a math wizard. This is my costume, is here. Yeah, okay, so. Any questions? So when did I cover this material? It was in the Wednesday video, right? If you haven't seen this yet, it's because you didn't watch the Wednesday video. I do talk about that in there. Not as much as here today, but I hope this there's like some homework problems where it says plug in like 2 plus I, right? So the point is, if you plug the complex number in and it's not 0, so I mean it is what it is, right? I think one of your homework problems is like plug it in, tell me what it works out to, or if it's 0, I forget the exact wording, but there's a homework problem which is probing your understanding of this theorem. What else did I say? I said synthetic division we don't have to do, right? So the synthetic division only divides linear factors into polynomials. So if you want to do synthetic division here, you have to do it twice. Once for the minus 3 plus 4i, and then again for the minus 3 minus 4i. And both of those calculations involve complex numbers. I think this is an easier way to do it because we don't really do complex numbers here, right? All we do at the start is recognize if I have this as a complex root, the theorem tells me that I've got x squared plus 6x plus 25 as a quadratic factor of it. And then we can do the long division thing and figure it out, right? Any questions? Right, well, so hopefully what I was planning, probably Monday for you guys. So what happens Wednesday?
Quiz.
quiz 2, right? So, so Monday, what I was going to do is try to do some, like break you guys up into groups and let you work some problems for yourself, yeah? And then you'll put the answers up on the board. So I'll probably break you guys into like 10 groups, and we'll find 10, you know, divisions on the board, and you guys will write up your answers, all right? And then at the end of class, like the last 20 minutes, like a lightning round, I'll go and I'll critique each group's answer and tell you how wrong it is or how right it is, and complain about your handwriting, stuff like that, you know? Like, oh, this is so ugly, you know, or, oh, this is so beautiful, or whatever it is, you know? No, and they're all going to be right, so the last 20 minutes is not going to be hurried. I'm not going to have to, like, fix all kinds of horrible math mistakes in 20 minutes. Like, it's gonna work, right? So you have that to look forward to, Monday? Yeah, extra credit. We'll see about that. Thanks, guys.